Hello everyone, I'm Pinelopi Moutzouri and I'm a postdoc at the group of Professor Lyndon Emsley at EPFL. So let's talk about proton resolution in organic solids. In solid-state NMR, the proton spectrostatic samples have line widths at the order of tens of kilohertz, and therefore proton resolution is practically non-existent. Since the 60s, MAS has tremendously helped with proton resolution. At the highest rate achieved today, proton spectra have line widths of about 200 to 300 Hz. However, the residuals of imperfect averaging prevent us from reaching Hertz or sub-Hertz line widths like the ones encountered in liquid-state NMR. In magic angle spinning, the main source of imperfect averaging are either misset of the magic angle or limited spinning speeds. For proton NMR, both of them lead usually to residual broadening. Here, we suggest that instead of trying to make a coherence average scheme perfect by minimizing errors, we could use an alternative approach to increase proton resolution. What we would like to do is parametrically map the errors in K-space in such a way that they can be removed in a multidimensional correlation experiment. We suggest a K-space where the KY axis corresponds to the evolution of the desired pure interaction, and the KX axis corresponds to the evolution of the error terms. In this space, any given FID will lie along a straight line at an angle phi to KY, where phi depends on how large the error terms are. As the spinning speed is increased, phi will decrease, since the error terms will progressively reduce while the isotropic term is constant. Here, we will demonstrate the method with a parametric fitting approach informed by average Hamiltonian theory. Now, we will introduce a model in which we make no assumptions about the shape of the isotropic spectrum, but we will assume that in MAS spectra, the error terms leads to an MAS rate-dependent symmetric broadening with a shape that is a sum of Gaussian and Lorentzian components, and that they also lead to an MAS rate-dependent shift. As you can see in the schematic, every MAS spectrum shown here in gray can be described by the convolution of an arbitrary spectrum shown in red, which is isotropic, with an MAS-dependent broadening shown in blue. In order to extract the pure isotropic spectrum from a dataset like that, we can fit this set of variable MAS rate spectra to the isotropic amplitude, the two broadening parameters, and the shift. Here, the fit performed on the synthetic data shown before accurately reproduces the original input function. So let's see how the method performs in experimental data acquired for a sample of L-tyrosine hydrochloride. MAS echospectra at MAS rates between 30 and 100 kHz in steps of 2 kHz were acquired under conditions of temperature regulation. Now, if we perform the fitting for the spectral region between 3 and 6 ppm, we extract a series of predicted MAS spectra at the same rates. And we also extract information about the decay of the Gaussian and the Lorentzian broadening as MAS increases. We will also extract the pure isotropic spectrum. The results are great, and for this sample, the method is providing a resolution enhancement factor of about 5. More importantly, is able to predict accurately the number of protons residing in the crowded spectral regions between 4 and 6 ppm. So let's see how the method performs in more samples. Cool, right? With that, I would like to acknowledge everyone in the Emsley group, and especially thanks should go to Bruno, Daria, and Lyndon for their contribution to the project. And thank you very much for your attention.